Let's do one last, more complicated example. Let's say that we want to approximate cosine of x over 3 using this fourth degree Taylor polynomial. It's fourth degree because the largest term is of fourth degree. So the question we want to know is, if we're using this as our approximation, what's the range of x values that we can evaluate using this approximation and have the error still be less than 1 over 10,000? So we've decided this is a fourth degree Taylor polynomial. So that means our original function is equal to our polynomial plus the remainder on the fourth degree Taylor polynomial. So we want to keep this remainder, which is the error, smaller than 1 over 10,000. So let's figure out what this error is equal to, so that way we can set it less than 10,000. All right, so we know that in general, r sub n equals the function evaluated, the n plus first derivative of the function evaluated at c divided by the n plus first derivative times x to the n plus 1. Okay, so for our example, we've got r sub 4. So that means we will have the fifth derivative of the function evaluated at c divided by 5 factorial times x to the fifth. All right, well, in all our other examples, the function was e to the x, so it was very easy to find out what is that fifth derivative. Now we've got this cosine function, so it's a little bit uglier. But don't despair, it's not too ugly. Let's work it out. So I know that f is going to be cosine x over 3. So that means f prime is going to be negative sine x over 3 times 1/3 because of the chain rule, which means that f double prime is going to be negative cosine x over 3 times 1 over 3 squared, because again I multiplied by 1/3 because of the chain rule. So the third derivative is going to be, let's see, when we take the derivative of cosine, we have negative sine again, so that cancels with the first negative. So we've got positive sine x over 3 times 1 over 3 cubed. So you can see the pattern here already. Well, actually, I guess we have only 2 more derivatives to do, so let's just do them all the way. So here we're back at, we're back at cosine x over 3 times 1 over 3 to the fourth, and then finally negative sine x over 3 times 1 over 3 to the fifth. All right, so we finally found the fifth derivative. Not so bad, though. It took under a minute. So let's plug that back in here to the error formula. So I know my error is going to be negative sine of x over 3, but what's x? X is what I'm evaluating my derivative at, so in this case it's c. So instead of x over 3, it's really c over 3. Divided by 3 to the fifth. That comes from the fifth derivative. And then we've still got a 5 factorial there, and we still have an x to the fifth here. All right, so that's the expression for our error term. And we know that no matter what x is, we want to keep this error term, well, rather we want to keep the absolute value of this error term less than 1 over 10,000. Absolute value because depending on what x is, the error might be positive or negative, but we want the absolute magnitude of the error to be smaller than that. Okay, so we don't know what c is, so let's put an upper bound on what this value could possibly be. We know that no matter what c is, this can't possibly get larger. Well, sine can't possibly get larger than 1 or smaller than negative 1. So what value is going to produce the largest overall number here? If sine is negative 1, then it'll cancel with this negative, producing a value of positive 1, which is the largest the numerator could ever be. So since that's an upper bound on the numerator, let's replace that with 1. So now I've got absolute value of 1 over 3 to the fifth times 5 factorial, x to the fifth, is supposed to be less than 1 over 10,000. Now we're in a good position to solve this inequality. Let's just multiply both sides by the denominator here. So I've got absolute value x to the fifth is less than 3 to the fifth times 5 factorial over 10,000. And then I'll take the fifth root, giving me absolute value of x is the fifth root of all of that stuff. If you evaluate what that is, you should, I think I did this. I think the answer comes out to be x is going to be between 1 point, oh, no, it's not true, I didn't do it. Okay, well, it's going to be 1 point something, and it's going to be negative 1 point the same thing. So you can evaluate that yourselves, and that's what the answer will end up being. Okay, there's a little bit of a wrinkle here. I don't know whether this was going to occur to you or not, but the wrinkle is, I said that this is the fourth degree Taylor polynomial, and that's true. This is also the fifth degree Taylor polynomial, because there are no odd degree terms in this Taylor series. So that means that if we include the fifth degree term is just 0. So strange as it might seem, this is true. These two approximations are the same. So that means we could also do this problem this way. It's going to be the fifth degree Taylor polynomial plus the remainder on that one. And if you go on to do the same process for this, you're actually going to get a different set of bounds for the error. I just wanted to reassure you that that's not weird or bad, and it doesn't mean there was a mistake. The important thing to remember is this term doesn't tell you what the exact error is, because we didn't know what the exact value of c was. If we knew what the exact value of c was, then we would have the exact error. Instead, because we have to do an upper bound on c, this when you work this equation out and when you work that equation out, both of them are upper bounds, and sometimes upper bounds are better than other upper bounds. They're closer, or as we say, they're tighter upper bounds. So either one is an acceptable answer. Obviously, you want the tightest upper bound that you can possibly get, because you want to reassure yourself that the error is in the smallest range possible. So if this actually gets you a tighter range for your possible error, then go ahead and use this one. It's not to say that this one is wrong. It's still an upper bound on your error. It's just not as good an upper bound on your error. So I think that's all I've got to say about that, and that should give you enough information to do the homework.